Welcome everybody. Today I'm going to be starting work on a new programming language. What I got over here is just a very simple setup for a C project. So I have a build file which will just run Microsoft Visual C compiler on this file with a bunch of flags. This basically just removes some warnings I don't like and telling it to use C++ latest standard, which is slightly weird, but this is how you enable MSVC to use the latest features of C, which I'm going to be using quite a bit. And the rest is telling that I want absolute path, I want debug information and stuff like this. I honestly don't remember all the flags myself. I'm just kind of copy pasting this from project to project. And this makes sure that I actually have Visual Studio Compiler available. Anyway, and in the only C file I have, I've set up a simple test. This is using BDD for C, which is a header-only BDD testing library that I developed for myself a while ago. It looks pretty much like all other BDD or DDD libraries that you might have seen in other languages, and I just really like that even in C I can use this kind of nice syntax and run my tests. Right now, obviously, it doesn't do anything. It just has a dummy check of foo equals foo, but still, let's run it and see that everything is fine. So the way we do it is with maybe build, which will build our file. Okay, great. And now we need to run it. So build the slash project. I'm calling it S, and you'll see why a bit later. Okay, so our tests pass, which is great. And let me move this over here so I have a bit more space for other stuff. And let me close the debugger for now. Good. So let me start first with a bit of explanation of how compilers usually work and what I will be doing a bit different for the way we're going to approach it, at least right now. So let me just add a bit of comment here. So usually what happens is you have your source code. That source code is then split in a bunch of tokens, which is called by Lexer, which splits it into tokens. And if we look into C, those tokens might be something like identifier, an open brace, a string, a number, an operator. And the reason why we want to do this and not just look at individual characters when trying to understand how your program is structured is connected to the fact that of how many combinations of things you need to look at, and we'll dive a bit deeper into this when we get to actual lexing ourselves. Then once you have these tokens, you put them in Parser, and this is usually the thing that takes the tokens. So it kind of if I do, let me actually do kind of C definition of functions. So Lexer would provide us an array of tokens. So this would be Lexer source. This would be our Lexer. This would be what the parser would look like. So it will accept token list and return us usually a node of abstract syntax. And all it is just saying that we take our source code and we take our tokens and turn them into kind of logical groupings of different operations. So if we just take this part over here and imagine what this might look like once we construct the abstract syntax tree, this would be kind of tree representation. And the important thing about abstract syntax trees is that they are constructed sort of in a reverse precedence order. So the operation that happens last will be at the root of the tree, and then the operations that happen first will be on the leaves. So in this case, you'll have something like root, which will be comparison, and then it will have on one side it will have a function call of like this identifier, and then it will have args which are literal. Actually, let me do this function call more explicit. So it was a function call, and then it has ID, and it has these strings as kind of arguments. And then on the other side of this, let me add another line here so it's more visible. So like we have this, and like this, right? So this is our tree, and on the other side of this tree would be just called literal, which just means we typed a number into the source instead of it coming from variable. And this is what our kind of abstract syntax tree would look like after it comes out of the parser for this particular line of code, this particular line. The reason that you want to do this is usually because it makes it easy, or it makes it easier to for subsequent code to understand the structure of your programs. Instead of kind of looking at a flat list of stuff, we can have things that operate on individual nodes of this tree and do stuff to them. So for example, if we look at the function call, okay, we know that at this particular point, our program is supposed to call function as their CMP, and then it's supposed to take these things as arguments to that call. And if we have another function somewhere else, it will have exactly the same node, so we can kind of recursively go through that tree and apply the same transformations to progress our program. After you have your ST node, if you are writing a compiled language and language that has types, you would usually do type checking. Type checking might just go through the tree and verify stuff. It might transform one tree into another tree. This is kind of depends on how the language is structured. But for simplicity, let's just say that that type checking will not transform trees. It will just check some stuff and tell us, is it okay? Like this is not actually the interface which you would want, because you want to have more information about what actually failed. But for simplicity's sake, this is what roughly it will look like. So we take a tree that comes out of parsing, and we then just ask to type check it. The next step depends a bit also from language to language, but once you know, okay, this is the structure of my program, I know that it's correct, and definition of correct is different between different programming languages. I would like to actually turn this into some working code. If it is a compiled language, that means I will need to turn it into bytes that processor will understand and can execute. And again, languages differ here, but majority of kind of existing compiled languages right now, such as Swift, C++, C, Rust, they all use another library called LLVM that will take a special representation and turn it into machine code, so you don't have to do it yourself. This has certain advantages and disadvantages, but let's just write it out there. But the LLVM cannot just take our abstract syntax tree and turn it into machine code. It needs its own what is called intermediate representation. So usually you would have another kind of path that takes our AST and turns it into that. So we'll have like generate LLVM IR. It gets our AST node and outputs it. Then we have generate machine code. It will take our LLVM IR and provide us with essentially this, just an array of bytes. Like as I mentioned, this step of creating LLVM IR or an immediate representation is there to allow us not to worry about how machine code actually works, and also allows to target the same code to multiple architectures. So you could run it on x86 or x86 64, like what you usually have on your desktop computer with Intel or AMD processors. Or you can just ask LLVM to generate code for ARM processors, which what powers almost all mobile devices right now. This is how things are roughly done traditionally. And also traditionally, this is sort of the order you would go about when you're creating your language. So you would start with a file, you would type some stuff, figure out how to turn this into abstract syntax tree, and then move on and on and on. This is not how I'll be starting this project. Instead, I'm gonna take all of this standard stuff and just not do that. What will happen instead is I will try to straight away jump into generating machine code, avoiding all these steps, and then use this machine code to drive further development of the language as fast as I possibly can. Eventually, we will probably want LLVM bindings and LLMIR there. Eventually, we will want to obviously to have some kind of text representation, so it's easier for us to interact with the language. But for now, we'll just dive right in and go to generating machine code and marking it as executable and calling it right away. This is otherwise known as just-in-time compilation, or JIT. So if you hear, for example, that JavaScript V8 engine, what powers Chrome and many other browsers, is using JIT, this is what it does. It kind of generates some machine code based on the JavaScript that you wrote and says to the system, okay, now actually these bytes that I've given you, you can consider them valid machine code and you can start executing them. I have done some stuff like this before, but I don't remember much how it works. So we'll just kind of go as we go. One big help for us will be a resource called bolts.ms, which takes a bit long. If you don't know, actually don't remember what is the main website. Yeah. So if you don't know about Compiler Explorer, it's a really amazing website that sort of allows you to type in some code in majority of popular languages. Like you see, you have a lot of them here. And it will show you the mapping from that code to generated assembly. And you can also like choose different compiler options when you do that. And generally it also like it keeps the mapping. So you see that I hover over num here and it shows me where it is actually in the output, which is super handy. And this is what we will be using to understand which kind of assembly instructions we need to generate when we first start up. But obviously we'll still need to turn these assembly instructions into actual machine code. So we'll see how we do that a bit later. And the first version that I opened, the codebolt.ms, this is just specific to Microsoft Visual compiler because it has to run on Windows, so I think they host their own version of this. It has a bit less options, but since I'm on Windows and I'm using that compiler, this is the version I'm going to be using for our project. Turns a possible question: why am I developing this version on Windows and not on any other platform like Mac or Linux? Windows actually is one of the simplest ways to generate binaries. So it's the format of the binaries is pretty straightforward. You also technically can run binaries without having to rely on C runtime. Also, that's not advisable. It's still possible. This is something that hopefully will help us get off the ground a bit faster. But let's see how it goes. Okay, so we have our Compiler Explorer. We are ready to start actually generating stuff. So what are we going to generate? The natural starting point for any language is usually writing out hello world, but that is actually quite complicated when you have to generate a machine code yourself and do all the kind of memory stuff yourself. So we will start with something even simpler. We will have what we want to do is to be able to generate a function that does not take any arguments, and that we'll call it the answer, and it will just return to us 42. This is all it needs to do. Actually, now I need to figure out how do I switch to x64, because I don't want to have 32-bit instructions. I want to have 64 bits. Well, I guess let's ask the internet how to do that. So svc 64 blank slash arc. Sounds promising. That is not what I was looking for. No, this is not what I wanted. $64. Configure recipe for 64-bit targets. That sounds good. Runtime. This is not very promising. Says it's an x64. I guess no. Let's do it. So the reason it's EX is because we actually ask it that this is a 32-bit output. So if we bring in here steady int h, then we can do int 64 key, and this should give us. That is not what I would expect to happen. Okay. Yeah. This is an interesting thing. So basically what was happening before is in x64 assembly, when you take a number and you put it into a processor register, if the number is smaller than 32 bits, then you can technically put it in the lower part of the register and override the whole register. If that sounds like, if you don't understand what it means, that's fine. We will go a bit deeper into how all this works later. For now, I just also needed to remember myself how it actually works. So yeah, we can do 64-bit. We have everything's fine. So this is roughly what we will do. And I think we will want this version of the instruction rather than the other one, but we'll see. So now we also need somehow to get actual machine code out of this. And I'm not sure if I can get this out somehow. So there is, like, we could look here, I guess, and generate ourselves. But for the first part of the setup, I would actually like something to show us what it will look like. And debuggers usually allow us to do this. The problem with debuggers is when you compile a function with optimizations turned on, then there is a big likelihood that it will end up being inlined into a source, especially a function like this, which is like, okay, it just does nothing, it returns a number. So compiler will actually recognize, okay, I just have this number, why don't I put it right in the source code or right in the output? But we want to preserve this function. We can do some tricks to force the compiler to keep the function there. But if we build it in with optimizations, debugging this code will be a bit awkward. On the other hand, if we build in debug mode, it will generate a ton of instructions that we actually don't need. It has to do with debuggability and kind of safety nets, I guess you can call them. So I'm not actually sure what this is setup we want to have to get to the bytecode. I guess let's just ask can ask the internet, say x64 assembly online. Okay, let's just do something. Okay, that looks promising. So we have this command. Say we want to move, I have to scrape up and go to rather than yeah. So this is what I wanted to see. If we look at this, happens, I believe is, so you might wonder, like, how do I even look at something like this? We'll go into assembly format instructions more as we develop this language. Just to give you some idea of what's going on, and I may not be 100% correctly here either. So 48 is just a prefix that tells the processor that it needs to operate in 64-bit mode instead of 32-bit mode. And you can see this quite easily. So if we copy this, which we'll need anyway for our code, so let's just put it right here. So if we instead go to here and change to this version, you can see that it does not have the 48 prefix. Anyway, let's do this again. And C7 is probably the opcode, and C0 is what's called modern byte that tells us just like what goes where. But I'm not sure about this one. And this part is actually our number. On majority of current day processor architectures, what is called little endian, which means that the bytes are ordered from the least significant to most significant. So usually you're like used to read numbers from right to left, but with bytes you have to read it the opposite way. And 2A is just 42 in hexadecimal encoding. And these are the bindings because I believe there is no instruction that will tell us, I just want to load 1 byte. Here's this. This sounds really promising. Okay, I can probably save this to Quarksbar. This is also something we'll use quite a bit. So we have our move instructions, and we have ret, which stands for return, which is just a single byte that we have to put in output. Okay, so we have our stuff. I can even do something like define, say, something 64 ret is this. And what it means, but for now, this is just some useful stuff that we will need later. Okay, we know the bytes that we need to put in to make our awesome function return us what we want. Now we need to actually tell system how to take those bytes and allow us to call them as a function. On Windows, the way we would do that is with function called virtual alloc that kind of gives you some a page memory, and you can tell what is allowed to happen to that memory. So you can say, okay, people can read from this memory, or I can read from this memory, or I can write from this memory, or the processor can execute this memory as machine code. The reason you would want to send these permissions is because generally you don't want your data to be executable, so you don't want to make it so it's just accidentally you kind of put something, like you read a file, put it into the memory, and then you kind of it's automatically marked as executable, and so uh, anybody can just make your program load file and then make that run the file that they loaded, which poses all kinds of security risks and other issues. Okay, so we build this function, and now I need to remember which flags do I actually need to use here. Memory protection. This seems like something you would want. Okay. Yeah, this is exactly what I was talking about. So you can mark what can happen to the memory. Okay, this seems like we are ready to start actually writing some code. I will, for now, just write it inside the test. It should return 42 or create a function that will return 42. So what do we need? We need some memory, as I said. So let's just say I don't like to use the standard C types, so something like int or char, because they can be different things and different, not just different architectures, they can be different things in different platforms. So for example, on Windows and on Linux, there are different things. So there is this include that you can do. We already showed in the code vault, that is std int. It kind of gives you more standard way of saying, I want a 64-bit integer, or I want a 32-bit unsigned integer. And then there is also std bool, which kind of gives you a standard definition of boolean because C doesn't have one. But besides bringing in std, which gives you types like int64, I can't type, int64t, you also I like the verbosity of that. It's a bit awkward to type, so usually what I would do is I would say type def. I was forgetting which order they need to be. I think it's like this: type def int64t I something similar for other ones. But for now, we also want u int 8 t here. You will notice me not be able to type this because I have a microphone in front of me, and it's a bit like awkward setup that I'm not really used to for now. So let's see how it goes later, and hopefully I can manage better in typing this. Okay. So we want some memory. As I said, will come from virtual alloc. Okay. and we can look at what arguments needs. So the first one is address. This kind of allows you to specify where exactly in virtual space you want your memory to be. We right now don't really care. I don't want to go into explanation what's the difference between physical and virtual memory. So we can mark the 0 like null. Next, we want size in bytes. We could probably also pass null here. We can pass something more explicit. Right now, we honestly don't care because we need like 8 bytes to make that function. So whatever, we just say 1024. In reality, it will still give us at least a page. So again, it really doesn't matter what we pass here right now, but it will become important obviously later. Okay, allocation time. I don't want to go into explanation what this does either. For now, let's just say that we want memcommit and memreserve. In very, very basic terms, if you, from what I understand, if you just say memreserve, you just say, I will want to use this memory in the future, but you can't actually use it. And when you do memcommit, you can actually start using this memory. And even though you say memcommit, what happens in reality, it doesn't actually give you the memory when you do that. So like this particular call, so the only thing it does is reserve some space. So the kernel reserves some space for you, but the actual memory allocation happens when you start writing to that memory. But not important right now. We don't care about this stuff for now either. So, but we do care about the protection. And we want our stuff to be sub 2 lines a bit more. So we want page read to write, and we want it actually looks like we want execute read write. Sounds good. So let's see if that builds. If it doesn't, I screwed up something. Let's see what I screwed up. Okay, this is one of the kind of. I'm always not sure if I should keep this warning or remove this warning. Basically, it tells me it's like, oh, you created this variable, but you're not doing anything with it. It's good usually to have in production system because sometimes it catches copy-paste errors where you're like, okay, I'm going to copy this part of the code and I'm just going to assign something different, but then I'm using the previous variable. Okay, let's just make it shut up. I think this will do it. Yeah. So this is more or less standard way of saying to compiler, yes, I know that this variable, this parameter is unused. Okay, so the code, at least it runs or it builds. Let's see if it runs. It runs obviously doesn't do anything because we just created the memory, but we didn't do anything interesting with it. Now let's actually write some stuff into it. So, and we'll do it in the most dumb way possible. So we'll just say memory 0 is 0x, or since I created is x64 rex w, or there. Let's just do numbers for now. So I have a bunch of bytes, and what I'm going to be doing is basically just taking these bytes and putting them into memory. that's all that happens. So we want to put them at the right positions. We have C7, C0, 2A, and this is a bunch of zeros. Okay, great. And the last one is this. This one actually would right away. So we did some stuff. So we executed this move of 42 into rex or AX register, A register, and then we return. Great. So we move some time to memory. Let's see if it builds. Does build. Great. Now, because our memory is execute, we should be able to just call it. Actually, let me show you what happens if I don't do that. So let me do just this for now. So we wrote some stuff. Now we need to tell C that this memory is actually something that you can call. And the syntax for casting to a pointer is really, really weird in C if you haven't encountered it before. Usually it is easier to comprehend when you do a type def of it. So the first thing you do is you put the return type of the function. Again, like that type. Then you say that I want to have a pointer, and then the name. So type def in. Now let's just call this what I called it in the Compile Explorer. So this is the name of our type def, and then the arguments, and we don't have any. Okay. Let me check if I have not screwed up. Yes. So now I can say that I can say the answer function. I'm also always confused by the syntax myself. So now we want to cast the memory to be this function. Then we want result. And we want to compute. So it should be something like this, if I'm not mistaken. Obviously, it isn't. What does it say? Oh, okay, that's actually fine. And now we can check the result is 42. This is what we wanted to do. So let's see how that goes. Let's build successfully. But if I do run this, I will run straight up in debugger because we will see an error once we do this. So let's try this out. Yes, this is exactly what I expected to happen. So our debugger says exception thrown, blah, 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 user mode data execution prevention, a violation at this address. What does it say to us? It says that you asked me to try to run some code in memory, but that memory is not marked as executable. I'm not sure if I can get into assembly here, but wait, no, it's not work. Okay, so this is fine. We know how to fix it. We just need to say it's okay for you to execute this memory. This is what it's like that. Let's try that again. And run. And everything is fine. Let's verify again. Everything is great. So, to help us, we managed to get some memory and write into it a function that can be called like any other function and get back the result that we want. It's great, and it's a great start. I think I will cut it here and continue in the next video.